Welcome to you from Chem Help ASAP. Let's talk about how coupling interactions are quantified as something called a J-value and reported in NMR characterization data. We can quantify the magnitude of coupling interactions between two hydrogen nuclei as a J-value. What is a J-value? To understand, let's look at the spectrum of this simple molecule. We have two different hydrogens in this molecule, the left proton and the right proton. Each has one neighbor, so both hydrogens appear as doublets. The distance between the peaks within each doublet is the J-value and communicates the magnitude of the coupling interaction. Note that the units on the x-axis are ppm, parts per million. If we took the difference between these peaks, the difference would be in units of ppm. J-values are not reported in ppm, but in hertz. To convert ppm to hertz, multiply the ppm difference between the two peaks by the frequency of the magnet in hertz divided by 1 million. That's per million. So if the ppm difference were 0.2 and the frequency was 400 megahertz, 400 million hertz, the J-value would be 0.02 ppm times 400 million hertz divided by 1 million ppm. The J-value would be 8 hertz. Let's determine the J-values for a simple spectrum, the spectrum of ethyl acetate. Okay, the first signal we'll study is the methyl triplet, this CH3 group right here within the molecule ethyl acetate. In the triplet, this distance is equal to the J-value, and this distance is also equal to the J-value. First, we need to determine the distance in ppm between these peaks. Normally, the spectrometer computer would pick these peaks and give you the exact ppm value, but we'll do our best to read them off the x-axis. By my eye, this leftmost peak is at 1.1726 ppm. The middle peak is at 1.1548 ppm. The ppm difference is 0.0178 ppm. This spectrum is simulated by nmrdb.org with a frequency of 400 megahertz. So 0.0178 times 400 million hertz divided by 1 million ppm is 7.17 hertz. This J-value is the magnitude of the coupling interaction between the right methyl hydrogens and the CH2. Let's now look at the CH2 quartet, which arises from these hydrogens. All three of these distances should be equal to the same J-value. If everything is working correctly, the J-value we calculate for this signal should be the same as the previous value of 7.12 hertz. The magnitude of coupling experienced by both sets of neighbors should be identical. Okay, the leftmost peak is about 4.1308 ppm. The left tall peak is 4.112 ppm. The difference is 0.0186 ppm. The J-value is 0.186 times 400 million divided by 1 million to give 7.44 hertz. Okay, 7.12 is not the same as 7.44, but the values are close enough based on the crude estimates I'm making for the ppm values. In theory, these other distances should also be about 7.44 ppm. All right, how do we report all this information? We report proton NMR data by first writing proton NMR. In parentheses, we indicate the solvent for the spectrum. Our spectra were simulated, but let's assume we used CdCl3. The frequency is 400 megahertz, close the parentheses, followed by a colon. We then put the delta symbol, which stands for chemical shift, and our most upfield peak. The center point of that peak is at 1.15 ppm. In parentheses, we list the multiplicity, T for triplet, comma, 3H for the number of hydrogens, the integration, comma, J equals 7.1 hertz, and close parentheses. That's it, comma. The next signal is at about 2.04 ppm, parentheses, S for singlet, comma, 3H, close parentheses. Note that singlets do not have a coupling, so there is no J value, comma, the midpoint of our last signal is at 4.14 ppm, parentheses, Q for quartet, comma, 2H, comma, J equals 7.4 hertz, close parentheses, and period. Not every journal uses this exact style, but I'll use something close to this style for reporting J values in NMR spectra. That's how we calculate and report J values in NMR data. Please like, subscribe, and comment. Take care.